Hi, in this video we are going to discuss how we use the determinant as well as some more direct forms for computing determinants. We've already seen how the determinant of any matrix can be found using elimination. We can express a matrix as an LU decomposition, PA equals LU, and the determinant of A can then be given by plus or minus the determinant of U, where the determinant of U is simply the product of its diagonal entries, and the sign is determined by the number of row swaps involved in making P. But are there more direct definitions? Are there definitions that do not require us to go through the process of elimination? We've already seen that these exist for the 2x2 and 3x3, that there are formulas that we can write down for the determinant, and there are ways to simplify remembering these formulas. In the case of the 2x2 matrix, A11, A12, A21, A22, the determinant is given by a splice, a product of the diagonal entries, A11, A22, minus a product of the off diagonal. So we add the diagonal, we subtract the off diagonal, A12, A21. Fairly straightforward to remember. For the case of the 3x3 matrix, there's also a direct formula. This is a little bit harder to just remember directly. There's a mnemonic we can use to help remember this direct formula. A11, A12, A13, A21, A22, A23, A31, A32, A33. A mnemonic known as the rule of Serres lets us actually express this determinant as a similar sum of slices. The first entry is the product of these three diagonal entries. The second entry, A12, A23, A31, is a product of these wrapping around to A31. And the third positive entry, we start here, A13, and wrap around to A21 and A32 to give us three positive products. And we can then subtract off three backwards products. A11, A23, A32 is the product that we get wrapping around this way, right? Starting here, carrying over to the next row, and so on. A212, A21, A33, we start here, we go backwards and wrap around to the last entry, and A13, A22, A31 is the anti-diagonal down the middle. So three positive terms slicing forward through the matrix, three negative terms slicing negatively through the matrix. If you like to remember this form, and the rule of Serres helps you, go ahead and do so. It is not necessary to remember that form. And for higher order matrices, for matrices 4x4 or 5x5 and so on, there is no such mnemonic. I actually recommend not spending a lot of time trying to remember this form unless you already have it internalized. Rather, let's think about more general ways to define the determinant that work for all size matrices. First of all, let's take a look at these definitions for the 2 by 2 and 3 by 3. And if we look at them carefully, we might see that they have a similar form. They both involve sums of terms, where each is a product of elements of the matrices. The 2 by 2 has products of 2 elements. The 3 by 3 has products of 3 elements. And in each case, the elements involved have a first index that follows the sequence 1, 2, 3, and so on. 1, 2, 1, 2, 1, 2, 3, 1, 2, 3, 1, 2, 3. The second indices have those same numbers, but not in the same order. 1, 2, and 2, 1. 1, 2, 3, and 2, 3, 1, and 3, 1, 2, and 1, 3, 2, and so on. The second indices are scrambled versions of the sequence 1 through n. This idea leads us to our first direct definition, based on the language of permutations. This is known formally as the Leibniz formula for the determinant. It has a rather scary looking form shown here. The determinant of the matrix A can be written as a sum of terms, where each of those terms involves a product of entries and a sign. Now, what do these extra notation in here that of mean? Can we walk through the meaning of this expression? Sn we're going to define as the set of all possible permutations of the set 1 through n. So just as an example of what this means, for the two-dimensional case, S2 would be the set defined by one sequence, 1, 2, and another sequence, 2, 1. The two ways of reordering the sequence 1 and 2. For 3, the set S3 is all the possible ways of reordering the set of numbers 1, 2, 3. And it turns out that there are 6 such orderings. That's what we mean by S, this set of the different ways we can reorganize the sequence of numbers 1 to n. We use sigma to mean any particular entry from this. Any single value, single set of orderings from these is given the term sigma. So what we want to do here, this sum over all sigma from this set, means we want to add up a set of terms where we have one term corresponding to each element from this set. Okay. This signum or signature or parity of sigma is a value that is either plus or minus 1. And it's given by the expression shown here. The parity of the permutation is -1 to the p, where p is simply how many times do we need to swap individual numbers to get back to the original sequence. The original sequence uses 0 swaps and so always has a positive parity. 2, 1 can be returned to 1, 2 by a single swap of numbers. It has a parity of 1. The sequence 2, 3, 1, in order to return this to the original sequence, we can swap 1 and 2, and then we would have to swap 2 and 3. 2 swaps gives us a parity of 1 again. This just gives the sign of the term. We then have a product over as many entries as there are numbers in this sequence. 2 for the 2-dimensional case, 3 for the 3x3 case, and so on. And the product is of the entries of A, where the first index is 1, 2, 3, and the second index is determined by the particular ordering that we've chosen. Sigma I just tells us the ith element of a particular permutation. So say for this one here, sigma 1 would be 1, sigma 2 would be 3, and sigma 3 would be 2. All right. And this gives rise to the definition for the 2x2, gives rise to the definition for the 3x3, and can give a definition for any size matrix. This is a very elegant result, but it is not in any way practical. The number of these elements is n factorial. There are n factorial different elements. Factorial is the product of all numbers equal and below this value. So 2 factorial is 2 times 1 is 2 elements. 3 factorial is 3 times 2 times 1, 6 elements. Right? Even when we go to the 4x4, 4 factorial is 4 times 3 times 2 times 1 is 24. The 4x4 determinant gives us 24 terms. We would have to think of what all of those permutations are. This is an incredibly messy way to compute determinants. We don't use this method, but I'd like you to know that it exists because it is quite a beautiful form in many ways. It suggests that there's something deeply meaningful about the determinant, and it's not just a tool that we can use. All right. Are there other ways that we can give direct expressions for the determinant that do not involve memorization or elimination? Let's go back to these two original, the 2x2 and the 3x3 formulas, and let's see if we can understand them a little bit better. Well, for the 2x2, we could write the 2x2 determinant in the following way, as the product of A11 with the determinant of a 1x1 matrix, A22. Now, a 1x1 matrix is just a scalar. The determinant is just equal to that value. Minus 1, 2 times the determinant of a 1x1 matrix whose elements are 2, 1. This seems rather pointless for just the 2x2 case, but the reason for writing this down might seem apparent when we go to the 3x3 case. If we look at the 3x3 case, I see that there are two terms, a plus and a minus, that involve A11. There's two terms, a plus and a minus, that involve A12, and there's two terms that involve a plus and a minus that involve A13. We could imagine factoring out this A11. And if we did that, we would get what would be left with A22 times A33 minus A23 times A32. That's just taking these two terms and factoring out the A11. Well, this now looks like a 2 by 2 determinant. It's a product of two terms minus a product of two other terms. And if we look more closely, it looks like this. A11 multiplied by the determinant of a matrix whose elements are A22, A33, A23, and A32. We can do a similar analysis to each of these other terms, and we get A22 multiplied by a determinant of another 2 by 2 matrix, A21 times A33 gives us this term here. A23, times A31 is what this should say here, gives us this term here. And we can write this last term in a pair of terms in a similar way. A13 times a determinant of this term, A21, A32, minus A22, A31, this term here. The 3 by 3 determinant can be written out as a sum of 3 2 by 2 determinants. The 2 by 2 can be written as a sum of 2 1 by 1 determinants. Perhaps this is generalizable. Before we do that, generalize to the n by n case, let's think a little bit about what these determinants are. How are they structured? This is our re-expression of the 3 by 3 determinant as a sum of 3 2 by 2 determinants, each multiplied by a value and with a sign that also needs to be taken into consideration. Let's now try to relate these back to the original matrix. Our original matrix, A11, with all entries here. What are the elements involved in this term? Well, we have a coefficient A11, which is this term, and we have a determinant of the entries A22, A23, A33, A32, and A33, which is this block of terms here. We note that the elements that we have here in this determinant are the ones that are left if we delete the row and the column corresponding to this coefficient. For the second term, we have a A12 and A12. The pieces that we're left with, A21, A23, and again, this is the same error that I had on the previous slide, apologies. A31, A23, and A33 are the pieces that are left when we delete the row and column corresponding to this entry, leaving us these pieces. The third entry, the third term, follows the same form. We have a coefficient and a determinant of the matrix that's left after we delete that row and column. Every term here includes one element from the first row, A11, A12, A13, and the determinant of the matrix that's left over if we delete that row and the column corresponding to whatever the coefficient we were working with is. So this tells us that seems to be a general rule for how we can construct this sum of matrices. We do see that there is differences in sign that we will also need to take into account. The general expression for how this works is known as the Laplace expansion, and uses a set of ideas known as cofactors. There are actually two ways that we can write the Laplace expansion. One is over an expansion on a row that we just showed. The determinant of a matrix A is a sum over all of the columns of the matrix, where each term in the sum involves an element from row I and column J, and the determinant of a matrix. We call this Cij the ijth cofactor of A, and it has a definition shown here. It involves a determinant of the matrix obtained when we delete row I and column J from A. The determinant of that matrix is known as the ijth minor of A. And it has a sign term, a sign determined by -1 raised to the power of I plus j. If we go look back at our previous result, when we had ij1, 1, we had a positive term. 1 plus 1 is 2. When we had 1, 2, 1 plus 2 is 3, we had a negative. When we had 1, 3, 1 plus 3 is 4, we had a positive. Even sums gave us a positive, odd sums gave us a negative. That's expressed here. -1 to an even power is +1, -1 to an odd power is -1. The example we showed expanded along the first row. It actually turns out that this expression works expanding on any row. We can choose to expand on the first row, the second row, and third row, and so on. And this formula always works. We can, in fact, also expand on a column. This isn't surprising. Remember, the determinant of the transpose of a matrix is exactly the same as the determinant of the matrix itself. Expanding along a row of a matrix is the same as expanding along the column of its transpose, and so it makes sense that the same definition should work. So we can expand along a column. In this case, we take a sum over all of the rows, but each of the terms looks exactly the same. A coefficient multiplied by a cofactor, which involves a sign term, plus a determinant of a matrix that we get deleting the corresponding row and column. The language of this might be a little bit sort of confusing. The language isn't the essential piece here. The essential piece of this Laplace expansion is the idea of how this can be used to compute a determinant. Let's go through an example to see how this works. The Laplace expansion particularly is useful for evaluating determinants when we have lots of zeros. Why is that? Well, it's because when we go to this sum over terms, any element that has a coefficient of 0, we can skip. Doesn't matter what the determinant is here, what the cofactor is, because if the coefficient is 0, it won't contribute to the sum. And so if we have either a row or a column that has lots of zeros in it, this sum will have very few terms. Let's see how this works out for a pretty big matrix, 5 by 5. How can we compute the determinant using a Laplace expansion? Well, let's start by expanding along a row or a column. The first step is to take a look at this and say, which row and or column has the most zeros in it? And that is either the first row or the first column. Both of these have 3 zeros. Every other row or column has more zeros than that. Right? The last row and the last column also work, but let's start with the first row. We go through this matrix and we express a sum taking the coefficient from each term. So coefficient 1 goes to a 1 here, and we take the determinant of what's left after we delete the first row and the first column. That gives us this matrix remaining, which is exactly what we have written here. This was the 1, 1 case, so it's a positive. We then move to the next entry, a 2. This was the 1, 2 case. So this was I equals 1, j equals 1. So it's positive. This was I equals 1, j equals 2. So it's negative. Coefficient of 2. And the matrix we have here is the one that we're left with after we delete row 2 and delete row 1. 2, 0, 0, 0. And the remaining 3 columns from the last 3 columns here. We've broken down this 1 5 by 5 determinant into 2 4 by 4 determinants. The power of the Laplace expansion is that we can apply this recursively. We can now evaluate this 4 by 4 determinant and this one using the same approach. Let's start with this first piece. So we have our coefficient 1 that we'll leave here. And now we want to express this with a similar expansion. Row 1 again has only 2 non-zero entries, so we can do this again. A coefficient of 1 for the first entry, and the determinant of the matrix that's left over, right here, minus 2 times the matrix that we get when we delete this column and delete this row, 2, 0, 0, 2, 1, 2, 0, 2, 1, as demonstrated here. We have our second determinant now to evaluate, minus 2, so we leave this same coefficient here. And we move on to this matrix. In this case, I'm going to expand down a column. Why? Because the first column has only 1 non-zero entry. The first row had 2. Expanding down this column, we'll only have 1 term, coefficient of 2, multiplied by the matrix that's left when we get rid of that row and that column. And that's the piece right here. All right. Before moving forward, this happens not infrequently, that as we go through this process, the same determinants might appear in the sums. And we notice, for example, this matrix here is exactly the same as this matrix here. And so let's simplify this expression. 1 times this determinant minus 2 times the same determinant gives us negative 3 times that determinant and negative 2 times this one. Right? Now we're down to the 3 by 3 case. If you happen to remember the direct form, you can go ahead and use that here, but it's not necessary. It's not necessary because we can always use the Laplace expansion to get these 3 by 3 determinants. We go through once again an expansion. So let's start with the first case, negative 3. Let's expand along the first row. We have a 1 multiplied by the determinant of what we're left with, the 1, 2, 2, 1 matrix. Minus 2 multiplied by the determinant that we're left with if we delete these, 2, 0, 2, 1, as shown here. For the second piece, again, we have our minus 2. Once again, the column is the one to expand on here because there's only one non-zero term. 2 goes here, multiplied by the determinant of the matrix that we're left with. In this case, once again, we have a pair of shared determinants, so let's simplify. Negative 3 times 1 times this determinant, minus 2 times that same determinant, give us negative 7 times that determinant. And the other piece, negative 3 times negative 2 times this determinant is plus 6 times this determinant. Now we're down to the 2 by 2 case, and so we can simply evaluate our determinants directly. Negative 7 multiplied by 1 plus 1 minus 2 times 2. Negative 7 times 1 minus 4. Plus 6 times 2 times 1 minus 2 times 0, 2 minus 0. This gives us negative 7 times negative 3 is plus 21, plus 6 times 2, 12. 21 plus 12 is 33. This recursive application of the Laplace expansion gives us a way to compute any determinant without using elimination. Now, it is actually a bit of a clunky way to do it if we don't have a lot of zeros. If we didn't have a lot of zeros, this first expression would involve 5 separate determinants, each of which is a 4 by 4 determinant, which would give us another 4 3 by 3 determinants. It gets messy very fast. But when we have a lot of zeros, this can give a fairly direct way to compute the determinant. This also, for the 3 by 3 case, isn't very messy and gives us an alternative to the mnemonic, the rule of Serres, to remember the 3 by 3 determinant. We can just apply the Laplace expansion in each case. Okay, so we've gone through now 2 more direct definitions of the determinant. The elegant but not very useful permutation-based definition, and the Laplace expansion approach. Right? But what use is this? We've also discussed how we can compute determinants through LU decomposition. Why bother? Right? Now, we've discussed how the determinant gives us an algebraic expression that tells us when a matrix is invertible. But in fact, elimination can also tell us when a matrix is invertible. We begin elimination. If we get a 0 row or a 0 column, we know we have a singular matrix. Computing a determinant appears to be more complicated than that. And so what's the point? Well, one application is that when if we have a matrix that has a lot of symbolic constants, letters that represent numbers or symbols that represent numbers rather than actually just numbers, elimination becomes messy. Right? When we have to keep track of all of the individual elements, elimination becomes very, very frustrating to apply. And we saw that when we tried to derive a general form for the 3 by 3. The Laplace expansion approach, for example, gives a much cleaner way to get a get an expression that tells us when a matrix will be invertible when we have these symbolic constants within the matrix, right? More than one or two. Right? This we are going to find to be very important when we discuss eigenvalues in our subsequent unit. There are also some other uses of the determinant. One of these is a direct definition of the matrix inverse. This is known as the classical adjoint or adjugate method of finding the matrix inverse. For any non-singular matrix A, the inverse can be found by the inverse of the determinant, 1 over the determinant, multiplied by a matrix known as the classical adjoint of A. This classical adjoint is the transpose of a matrix that's made up of all of the cofactors of A. We just discussed how the cofactors of A are involved in this Laplace expansion method for computing a determinant. The cofactor ij is the determinant of the matrix that we get when we delete row I and delete row j, so a slightly smaller matrix with a sign defined by -1 to the sum of I and j. This is a number, a single number. The determinant of a matrix is a scalar multiplied by a scalar. So the matrix that we get by making every element a different cofactor, when we take the transpose of that matrix, we get the classical adjoint. You do not need to remember this form to memorize this form directly. Right? You should be aware, however, that it exists and be able to use it if you need to. How can we use this? Let's think about the 2x2 case. Right? This lets us actually derive a general form for a 2x2 inverse that doesn't actually require us to do any work. We use symbolic variables for our 2x2 matrix. The determinant of this matrix, of course, is given by the positive product of the diagonals minus the product of the off diagonals, so our determinant. And our various cofactors are found by taking the appropriate slices. And because we have a 2x2, when we take those, remove the relevant row and column, we're left with just a scalar. So for 1, 1, 1 plus 1 is a positive number, so we have a positive term. And what number we get, we delete the first row and the first column, leaving us D. When we have for the 1, 2 entry, first row, second column, we delete the first row and the second column, we're left with C. But 1 plus 2 is an odd number, so it's negative. We end up with negative C. For the second row and the first column, delete the second row and the first column, we're left with B. 2 plus 1 is odd, so we get a negative term. And for our last cofactor, we delete the second row and the second column. We're left with A. 2 plus 2 is a positive, is an even number, so we have a positive term here. C is the matrix whose entries are these cofactors. D for 1, 1, negative C for 1, 2, negative B for 2, 1, and A for 2, 2. The inverse is then simply given by 1 over the determinant, so 1 over AD minus BC, multiplied by the transpose of this matrix. So the diagonal entries remain the same, but the off-diagonal entries swap positions. This gives us a general form for the 2 by 2 matrix. Actually, the same general form that has been demonstrated in the book earlier, you can derive from elimination using symbolic elements. We can try to do the same thing for the 3 by 3. We can construct our general matrix, compute the determinant of this matrix, and then go through and evaluate the various cofactors. Delete the first row in the column gives us a 2 by 2 determinant, positive. Delete the first row and the second column gives us a different determinant, negative, and so on. Now, if we try to do this, we have to construct a matrix, a 3 by 3 matrix, where every element is one of these cofactors. There's 9 elements. This means we need to compute 9 2 by 2 determinants. 2 by 2 determinants aren't particularly messy, right? They're just a sum of a difference of 2 products, but that's still 18 different products we would have to compute and work all of these. It is going to give us a messy form. This is not an efficient method to use. Right? This is why we never write down a general form for the arbitrary 3 by 3 determinant. It's just too messy to work with. However, this can be helpful if we have a matrix that isn't completely filled with symbolic constants, but has more than 1 or 2, and would, if we have maybe only 1, we might be able to go through elimination. But if we have 3 or 4 symbolic constants in here, elimination is going to get messy. Perhaps this adjoint method, this classical adjoint method, might be helpful in giving us an analytical form for the inverse in terms of some of these symbolic constants. What other uses are the determinant? There's also a result known as Cramer's rule that allows us actually to directly solve for linear systems without going through elimination using determinants. Cramer's rule is expressed as this. If we have a non-singular square coefficient matrix A, the linear system AX equals B has a solution given by the expression here. Each entry xi in the solution is a ratio of 2 determinants, a ratio of a matrix of the determinant of a matrix we will call BI, and a matrix and of the original matrix A, where BI is an interesting matrix. It is the matrix that we get by replacing column I of A with the right-hand side. So if we think about A as being made of a set of n columns, the ith column here, we replace that one column with B, leaving all of the other columns exactly the same. That's what we mean by BI. The determinant of this is the numerator in this form. The determinant of the original matrix is the denominator. Once again, I do not expect you to memorize this form, but you should know that it exists and be able to use it if needed. Let's go through an example, again, the 2 by 2 general case, we can use this to actually give us a general form for the solution for any 2x2 system. We made a very, very general system. AX plus BY equals K, CX plus DY equals L. In matrix form, this gives us a coefficient matrix A, B, C, D, and a right-hand side KL. How do we use Cramer's rule? Well, the determinant of A, of course, is AD minus BC. Our B1, we replace the first column of A with KL, so we get KL BD, and we compute its determinant, KD minus BL. Our second B matrix, B2, we replace the second column of B with KL, so it gives AC KL, and the determinant is AL minus CK. Then we have a direct form for the first element, or so let's call this X equals X1, B1 over A, the determinant of B1 over the determinant of A, KD minus BL over AD minus BC, Y equals X2 is the ratio of the determinant B2 over A, determinant of A, AL minus CK over AD minus BC. A general form. Once again, if we were to try to do this for the 3x3 case, to come up with a general form for the solution to a 3x3 linear system, it becomes really messy. We have 3 different solutions. Each one, this is the, what we would want to have is xi is the determinant bi over the determinant of A. This was the classical adjoint entry here rather than the Cramer's rule entry here. And so what would we need to solve for this? We would need to compute the determinant of A. We would need to compute the determinant of B1, where we replace the first column of A with B. We would need to compute the determinant of B2, where we replace the second column of A with B. We would need to compute the determinant B3, where we replace the third column with B. This involves evaluating 4 different 3x3 determinants. Each 3x3 determinant is going to involve a sum of 6 different terms. That means there's going to be 24 different products we need to evaluate here. And each of these ratios is going to be a ratio of 6 terms over 6 terms. It's going to be messy and it's going to be very inefficient. It's much faster to solve a system using elimination than using some sort of a direct form like this. However, once again, if we have a system that has a lot of symbolic constants in it, maybe not a full general system, but one that has a number of symbolic constants, this can be a way to get a solution in terms of those constants, which can be helpful in certain circumstances. All right. This sort of just extends on that. For the general n by n case, we need to compute n determinants. Each of those n determinants involves n factorial calculations. Right? That means that the number of things that we need to do in calculating solutions with Cramer's rule is some n times n factorial, which is a very, very large number. It's not an efficient way to solve systems, but can be useful under some circumstances. So what have we seen? We've now seen the the determinant provides a set of tools that allow us to write analytical expressions for the singularity of a matrix. That really is what the determinant is. If the determinant is 0, the matrix is singular. For the inverse of a non-singular matrix, the classical adjoint method. For the solution to a system of equations with a non-singular coefficient matrix, Cramer's rule. None of these methods are well suited for simply solving general systems with numbers. Elimination is faster for everything except for maybe the smallest 2x2 systems. If you want to know if a matrix is singular, it's often easiest just to do elimination and see if you get a row of zeros. If you want the inverse, it's generally easier and faster to use Gauss-Jordan elimination. If you want to find the solution to a system of equations, even if you have many right-hand sides, it's generally more efficient to use LU decomposition and then use that to solve for different right-hand sides rather than to write a general form. However, when those expressions, when the matrix involved has symbolic constants and we want general analytical expressions for these values, that's where the determinant becomes useful. All right, with that, we've gone through the content part, the conceptual part of this unit, our discussion of the determinant. There are worked examples showing how we apply things like the Laplace expansion, Cramer's rule, the classical adjoint method in an accompanying worked example video. Thank you and goodbye.